electromechanical systems are devices and systems of the size of microns. How much is a micron? If you look at a hair, a single hair, and the thickness of that hair is of the order of about 100 microns. So we build devices of that order and study them, and a nano electromechanical device is 1000 times smaller than even that.
In my lab, we work on microelectromechanical systems with a special focus on piezoelectric transduction. So these MEMS are very tiny devices which has a large spectrum of applications, starting from devices such as accelerometers and energy harvesters, which have their operating frequency in few hertz, to gigahertz devices, which have applications in RF communication, to quantum. So in the lower frequency range, we work on devices such as energy harvesters, accelerometers, etc. And when we scale up the frequency, we work on devices which has applications in the RF communication and quantum communication as well.
Some of the faculty members who work in this MEMS and NEMS also are engaged with other faculty members in other thematic areas, right? For example, we are working to kind of integrate MEMS devices, MEMS or NEMS devices with charged superfluid helium, right? So to do sensitive quantum measurements, right? So that's one area where we are cutting across themes to work together to do something novel. We're working with people in photonics, where we bring together MEMS devices, NEMS devices with on-chip photonics and try to integrate them together, do some optomechanics or quantum optomechanics, those kinds of things.
In our lab, we mostly work on MEMS sensor technology. This is the technology which produces extremely small scale sensors. That's what is going to power IoT. So in all these sensors, there is one part which is about design. How do you design these tiny things? The second thing is, what kind of material palette do you use for this? So sometimes we also have to work on developing those materials. For example, we have been working on piezoelectric MEMS sensors, and there thin films of piezoelectric material have to be developed. It's not easy to integrate them in stack of other materials which are typically used in MEMS technology.
Piezo MEMS based systems are a multi-billion-dollar industry, and what we are doing is that we are taking the technologies that are developed from other countries and that are being used in our phones. So what we target to do here is that we can develop these technologies in the lab, for example an oscillator or filter, because larger the bands that we go, larger the components, and what we can do is that the technology we do in this lab can be transferred to the industry, wherein they can scale up the production and they can tie up with the telecom industries and provide these to the mobile manufacturing companies as well.
How do we develop new materials that can be used for these devices? How will these new materials affect the noise and other properties, right? We also work on NEMS, where we look at how to make smaller sensors, more sensitive sensors. We are exploring newer materials like 2D materials, graphene, MOSU. We are using those to make sensors. We are also working on things like nonlinear dynamics with these devices.
We work on all kinds of sensors, including gyros, for example, MEMS gyros, which are just on your smaller than the fingernail in packaged condition. We work on acoustic sensors, ultrasound sensors. We work on agricultural sensors. We have photoacoustics that we do. We are developing a field of ultrasound spectroscopy using these tiny transducers. We make these transducers and embed them in microfluidic channels so that we can pass fluids over the channel and interrogate the fluid with these transducers. We can put lots of them together so that you can do spectroscopy. So for doing this entire chain, from design to fabrication to characterization to packaging, the entire chain was to be done in one place. And for doing such a thing, you need not only a comprehensive fabrication facility, but a comprehensive suite of all kinds of characterization facilities, whether it's optical characterization, mechanical, material characterization. or electrical characterize. You need a facility where not only you can produce these, not only you can make them, but you can also measure what they are doing. You know, very, very tiny vibrations. How do you measure that? So we do that with laser Doppler vibrometry. And that's what we could achieve by bringing interdisciplinary teams together.
First part of our research was sort of more of researchy science aspect to it. Second part is quite practical. And the third is where everything comes together, building a system out of it. Remember that MEMS and NEMS have a S in the end, and that stands for system. So to build a system, we have to think about what kind of circuitry that needs to go with our device and what kind of eventual, not just the small package, but the full circuit packages that comes along with it. And that's not so easy to do because we make these devices in a very clean environment called a fabrication facility, a fab, and we build them there and we take them out. Right? We take these devices out, and what's going to happen to these if we take it out in the air in which we are currently standing in the atmosphere? Then they get clogged up. Right? That's really bad for these devices. It's like taking a fish out of water. Make a product, you need to package it, you need to cover this. It's like taking the fish out of the ocean and putting it in some sort of a container with water in it, with some special packaging, right? So you preserve it. So we work on packaging of MEMS devices. There are different ways of packaging. There is a particular kind that our group specializes in. It's called wafer scale encapsulation, where what we do is the entire device where when we are building this device in the fab itself, we actually develop the package in the fab itself. So that now when we take this device out after cutting it out, it doesn't see the world anyway.
And that is where this, the technology of heterogeneous integration comes into play, because we cannot miniaturize these devices any further, and we really need to think about the packaging and system integration aspect to take the benefit there and to look into miniaturization of the overall system, how we make the overall system small. Till now, most of the people in the world have been looking at miniaturization of individual devices where they're looking at making things smaller, each device smaller. But there has been no effort towards miniaturization of the overall system. And this is where we are looking into a development of packaging and integration techniques through which we are looking into miniaturization of the overall systems.
But very interestingly, you can find applications of this kind of overall theme in artificial intelligence as well, where we can build a hardware-based artificial intelligence systems.
All our work through technology goes from science to society.
Everybody in this department has this sort of viewpoint that eventually we need to take this into something that translates into a product. We not only deal with one kind of field or area, but you have multiple disciplines coming together, and it is the epitome of bringing together various sciences and building something amazing out of it.